Hello and welcome everyone to day 46 of our low-level design journey. Today's session is incredibly important and honestly quite exciting. We are going to dive deep into designing for concurrency. Concurrency is one of those topics that can really make or break the performance and reliability of your systems. Let's explore how to design systems that don't just work but thrive in the real world where multiple things happen at once. Let's begin by setting clear goals for today's session. By the end of this lecture, you will have a strong grasp of why concurrency matters so much in system design. You will learn about the key challenges it introduces and the key techniques we have to safely and efficiently handle concurrent operations. We will also go through real-world examples, practical design patterns, and even some hands-on exercises that you can try yourself. So get ready, today is going to equip you with critical skills for building scalable and robust applications. Alright, first things first, what exactly is concurrency? In simple terms, concurrency means that multiple tasks make progress at the same time, not necessarily finishing at the same time but progressing. It's important to differentiate concurrency from parallelism. Parallelism is when tasks are executed physically at the same time, for example across multiple CPU cores. Concurrency on the other hand is a logical structure. It's like two people working on different parts of a document. They may pause, switch tasks, come back, but from the outside it feels seamless. In design, we focus on structuring our code to handle multiple ongoing activities, whether or not they physically happen at once. Now you might wonder, why do we need to make our systems concurrent at all? The short answer, responsiveness and scalability. Imagine an e-commerce platform during a flash sale, thousands of users hitting buy at the same time. Without concurrency, your system would handle these requests one by one, leading to massive delays, frustrated users, and lost sales. Concurrency allows different parts of the system, like payment processing, inventory updates, and confirmation emails, to move forward simultaneously. This is not only improves user experience but also ensures that the hardware resources like CPU and memory are fully utilized. But of course, with great power comes great responsibility. Concurrency is tricky. One major risk is race conditions, where two or more threads access shared data and try to change it at the same time. Then there are deadlocks, a classic nightmare where two threads wait forever for each other to release resources. We also face starvation, where some threads might never get a chance to execute because others hog the resources. And debugging these issues, it's often much harder because bugs in concurrent systems are usually intermittent. They don't always show up in testing. Understanding these challenges is the first step toward designing safer, better systems. Thread safety is absolutely crucial in concurrent systems. It simply means that no matter how many threads access a piece of code or data, the outcome is correct. There are several ways to achieve thread safety. You can use thread safe data structures like concurrent hash map. Another smart technique is using immutability. If objects can't change once created, you eliminate a whole category of paths. And when shared mutable data is necessary, synchronization techniques can ensure that only one thread can modify it at a time. Always remember, designing for thread safety upfront saves you from painful late-stage debugging. One fundamental tool for thread safety is synchronization. Using locks, we can make sure that only one thread can access a critical section at a time. A simple mutex or mutual exclusion lock is like a do not enter sign for other threads. For better performance, especially in read-heavy scenarios, we can use read-write locks where multiple threads can read simultaneously but only one can write. But be aware, locking comes with overhead. Locking holds for too long can cause bottlenecks and even deadlocks. Good design keeps critical sections as small and efficient as possible, locking only when absolutely necessary. Deadlocks are like traffic jams, where every car is waiting for another to move, but nobody moves. They usually happen when multiple locks are acquired in different orders across threads. To avoid deadlocks, always acquire locks in a consistent global order. Alternatively, use lock timeouts. If a thread can't get a lock in a reasonable time, it backs off and tries again. Sometimes it's even better to rethink the design to avoid blocking altogether, for example by using non-blocking algorithms or concurrent queues. Atomic operations like magical moves that happen instantly without interference. They are operations that either complete fully or not at all, making them perfect for concurrency. For example, updating a counter can be made thread safe using an atomic integer instead of synchronizing manually. This not only makes the code cleaner but also faster because atomic operations use low-level CPU instructions optimized for speed. Wherever possible, prefer atomic data structures to manage shared state safely and efficiently. Concurrency should not be an afterthought, it must be built into the design itself. Design patterns like producer consumer help separate the generation of tasks from their execution, smoothing out load spikes. Task queues combined with worker threads allow the system to balance work among multiple processors, and frameworks like Java's executor service or Python's Essentio provide elegant abstractions over raw threads, making it easier to manage resources without reinventing the wheel. Design smart so that your concurrency model is predictable, scalable, and easy to maintain. Let's talk about some key patterns that help us design concurrent systems more efficiently. The thread pool pattern. Instead of creating new threads for every task, we reuse a pool of threads, saving overhead. The future promise pattern. It allows a thread to start work asynchronously and later retrieve the result. And then there's reactive programming, a completely different paradigm where systems react to streams of events asynchronously, allowing even higher scalability. Each of these patterns solves specific concurrency challenges, and choosing the right one depends on your application's needs. Concurrency is not a theoretical concept, it's everywhere. Think about a ticket booking system like Book My Show. Hundreds of people trying to book the same seat. The system needs to handle those requests in real time, ensuring fairness and avoiding double bookings. In stock trading systems, milliseconds matter. Concurrent operations must be handled with utmost accuracy and speed. Messaging apps like WhatsApp manage typing indicators, message deliveries, media uploads, all happening at the same time without blocking the user experience. Mastering concurrency prepares you to build this kind of real-world high-impact systems. Now it's time to get hands-on. We will implement a simple concurrent counter. First, we will use a synchronized method to implement the counter safely. Then we will switch to using atomic integer and you will notice a significant performance boost. After that, think about how you would design concurrency for a shopping cart checkout system where multiple users can add or remove items, apply coupons, and check out all at once. It's a great exercise to test both your creativity and your technical skills. So let's summarize today's key points. Concurrency can dramatically improve the responsiveness and throughput of your systems, but it also introduces risk, race conditions, deadlocks, and difficult to reproduce paths. Good concurrency design focuses on minimizing shared mutable state, preferring immutable objects, using safe synchronization techniques, and stress testing extensively. And remember, you don't always need to reinvent the wheel. Use proven libraries and frameworks wherever possible. For those of you who want to dive deeper, even I highly recommend Java Concurrency in Practice by Brian Boards. It's considered the Bible of concurrent programming. Joshua Broad's Effective Java also covers concurrency fundamentals beautifully. Google's official thread safety guidelines are great for best practices, and if you are working in Python, learning Asyncio and threading is essential. Finally, explore reactive programming frameworks like RxJava, Reactor, or even Kotlin's coroutines for a modern approach to concurrency. Thank you for your attention.